Hi class, welcome to this lecture on small scintillation detectors. This lecture is on the well counter. These are the learning objectives. The well counter is used for receipt of radioactive packages, leak testing, looking for removable contamination, and small sample counting. It is important to note that these are all wipe testing procedures, and the small samples may not be wipe tests. They may actually be small tissue samples, but the size of that hole on the well part of the counter is only big enough to hold like half of a test tube. It's only big enough around for a test tube to fit, and then the test tube only goes in about halfway. So really small tissue sampling, if that's what it's used for. But the majority of the time in nuclear medicine, we're just using it to count wipe tests. And so if we're looking for leaks on any of our sealed QC sources, receipt of radioactive packages where you actually wipe the package with the wipe, and then both of those things, receipt of packages and leak testing, are looking for removable contamination. Anytime you do a wipe test, that's what you're looking for. I have the word removable standing out there a little bit because removable contamination is the contamination that's on the surface of things, where if you touch it, you're going to get contaminated and then you're going to spread it. And surveys are used for looking at the overall exposure of radioactivity in the area, but the actual wipe tests are looking for removable contamination. That's a really important distinction between wipe testing and using a GM survey meter, is that the wipe test is going to find if there's removable contamination on the surface. That's the contamination that if you touch it, it's going to spread. The units for the well counter are in counts per minute or counts per second. And then some newer machines will convert that to disintegrations per minute for you. In order to convert to disintegrations per minute, you have to know the overall efficiency of that specific well counter. And so some of them have it programmed in and will can display it in disintegrations per minute. Others do not have it built in, and you would have to know the efficiency of your instrument and convert it manually to disintegrations per minute. So there are a couple different types of well counters. The one here on the left is a wipe test counter. It's the same design. It's a small scintillation detector. It's got one PM tube in here, coupled with a preamp and an amplifier, and then the wiring that goes to this readout. In the wipe test counter, it's a very, very simple machine. These are typically single channel analyzers. Some of them are multi-channel, but it's very simple, and you basically, it just counts the number of counts in a wide window per minute and displays that, and it doesn't really do much else. This Biodex one here on the right is a well counter. This is an Atom Lab by Biodex. These are much more complex in their display, but the inside of it is still the same. That well has, it's lead lined, it has one PM tube, preamp, amplifier, and then the pulse height analyzer and wiring and all of that. So the actual well part is the same on the inside. The difference is how it's produced here. So, or how it's displayed. So in this one, you can see the spectrum graph. What's red there is what's in the window. And you see the dotted lines going up here for lower level discriminator and upper level discriminator. And then it's kind of showing you in disintegrations per minute if it passes. And that's too small to see, but it's showing you the count rates and everything. The main point is that these newer well counters will display the spectrum graph and convert to disintegrations per minute, whereas these older wipe test counters are much more simple and really don't do all that. So the basic principles of scintillation detection, to scintillate means to create a spark. So a scintillator is any material that can release a photon in the ultraviolet or visible light range when an excited electron in the scintillator returns to ground state. Scintillation photons are detected by the photomultiplier tube and converted into an electronic signal. Each photon interaction produces many scintillation photons, and the total counts represent the energy. I do want to point out that whether it's single or multi-channel analyzer, it can detect more than one photon at a time. It will detect all of them that are interacting with the crystal at any given time. So this is what the inside of these well counters look like. This image here is an older Capintec. Notice this one doesn't really have enough room for a spectrum display. It is still a well counter. It's going to tell you the counts per minute. So this part is the well up top, but the side view here shows you what's going on in the inside of the well. The sodium iodine crystal kind of surrounds the sample. The sodium iodine crystal is in a U shape. And what's blue here is the sample that goes inside of it. In reality, the test tube is really going to stick up further than what the tube is. So it's just going to nestle down in there. That crystal is coupled directly to the PM tube. And then after that, you have the preamp, the amplifier, and the pulse height analyzer. And then this is the lead shielding that surrounds it. This is important design for a couple of reasons. For one, that crystal is surrounding the sample. That's one of the reasons that the well counter is our most sensitive equipment of all nuclear medicine equipment in the whole entire world ever. It's really sensitive because that crystal is surrounding the sample. So remember, radiation is released isotropically in all different directions. With the crystal kind of surrounding it, the only photons you're losing are those that are coming right out the top. Everything else is being captured. That lead shielding also, that serves two purposes. One is to protect us, radiation safety wise. If the sample has a lot of radiation, it's not going to penetrate through and expose us. But also, that lead shielding helps to scatter and deflect the photons back towards the crystal. So this is the other reason why the well counter is our most sensitive instrument, is because this lead shielding that's out here is going to direct those photons that did pass through the crystal without interacting with it back to the crystal. So you'll get maybe sometimes a little more scatter and things like that, but that lead shielding is going to serve a really good purpose to trap those photons so that they do interact with the well counter crystal. Now, this is just explaining the scintillation process. Again, this is in chapter 2 of your Prickage's instrumentation book. And this conduction band, valence band is showing you what's happening at the physics level inside the crystal, inside those sodium, iodine, thallium atoms as it's interacting with them. And it's actually the thallium activated sodium iodide molecules that are that is interacting with it. And so some of the free electrons created by the gamma ray interaction have enough energy to jump from one valence shell to another. Once in the conduction band, the electrons migrate to the activation center, excited state orbitals, and then the holes in the valence band. The transition of the electron from the activation center to excited state produces that scintillation photon via photoelectric effect. So this conduction band and valence band are just different electron shells within an atom, and is basically telling you how it really, one electron, it gets so excited that the electron will move to a different valence state, and that energy difference that's there is what's given off as the scintillation photon, that UV light that ends up making its way to the photo cathode of the PM tube. So it's just showing you how that interaction with matter is happening. These are kind of different words for saying the same thing. It's just telling you it's moving from one electron shell to the other. And then as it does that, it's releasing a photon. This is just kind of explaining photoelectric effect using different terminology. So keep that in mind. All right, so this is showing you really what I said on a previous slide about the photons interacting with the crystal. You'll notice that these photons coming out the top are the only ones that are really not getting trapped by the crystal, because even this one that makes it through, it's probably going to interact with the lead and backscatter back to the crystal. Some of them, if they're high enough energy, will escape through that lead shielding, especially if whatever you're sampling is really high energy, like PET, for example, like a PET radionuclide, then it's more likely to penetrate. But the well counter is very efficient at trapping those photons, and that's why it's more sensitive, right? The shape of the crystal, the geometric efficiency, and also this lead shielding contributes to that also. Now, some well counters actually have a lead lid that are placed over the sample, and that lead lid helps to deflect these photons that would come out the top right back to the crystal. So why do we use sodium iodine thallium? Well, it's relatively dense, so it's a good absorber, and it's efficient at interacting with photons. We say it's efficient, but it's relatively efficient, typically about 30%. It's transparent to its own scintillation photons, so those scintillation photons don't really react with the crystal. They travel straight to the PM tube. There's a little loss of scintillation light by self-absorption, but not much. And then it can be produced into large plates for the entire surface of a camera face. And scintillation light is well matched in wavelength to peak response of a PM tube. So sodium iodine thallium is dense enough that it will stop our lower and medium energy photons. It is transparent enough to its own photons that the scintillation photons can pass through it without interacting. And then it's affordable to make into larger plates. So it's affordable and readily available. And then once it actually gets to the PM tube, that wavelength is well matched to the peak response of the PM tubes. So it makes it easier to manipulate and detect our photons, our gamma rays with it. And sodium iodine thallium is used for pretty much all of our scintillation detectors. We do have newer instruments, and especially our cameras that are solid state detectors, and they have like no PM tubes, because they are just basically a different type of crystal coupled directly to a digital counting pad. And they're a lot more electronic. So there are some digital detectors out there that are coming to the market. We'll talk about that science in the very last week of class, but for the longest time, and still now, our small instruments are sodium iodine thallium, and most of our cameras are also. The solid state and digital detecting is really just within the last couple of years that it's been able to be produced. So a lot of the cameras that you're going to see in the clinical setting or work with still have the same technology with the sodium iodine thallium crystal. Some disadvantages of the sodium iodine thallium crystal, though, is that it's fragile, it's hygroscopic, the exposure to moisture or humidity causes a yellowish discoloration that impairs the light. Keep in mind that is almost like a giant salt block, so it can't get wet, and that moisture will really affect the crystal. And then the predominant interaction above 250 is Compton scattering, and larger volumes of crystal are needed for adequate detection especially when you have higher energies. So it's really great for our low energy stuff in tech, but once you start using high energy, and PET is 511 keV, it's really not good for PET, so it's not used in PET scanners. We have denser crystals for that. But over 250, keep in mind with those higher energies, the predominant interaction is going to be Compton scattering. And we do image with energies higher than that. I-131, it has 361 keV, and that one, the predominant interaction for that one is going to be scattering, and we have terrible image quality when we image with I-131, partially because of that crystal. It also has to be hermetically sealed. Any interaction to light can help wear down that crystal over time. Never ever crack a crystal. You're probably not going to do that unless you have a really big accident or you're just not great with your handling your instruments and you're careless. But accidents do happen. If you crack a crystal, it's often cheaper to buy a new instrument than to replace the crystal in the existing one. And it is usually made of sodium iodine with thallium doping. The PM tubes we've talked about before. The photocathode is closest to the crystal. This is made of a thin layer of a photoemissive material, usually a metal alloy, and it absorbs scintillation photons and emits electrons into the PM tube. The focusing grid provides an electrical field that directs electrons towards the first dynode. And then in the dinodes within the PM tube, each of them have a higher positive potential than the last. Each of those dinodes has their own high voltage supply to it, but the high voltage is slightly higher as you progress through the PM tube. So it might be 20 at the first dynode, but 150 by the time you get to the last one. Each of them has a slightly higher high voltage supply to it, a higher potential. They are also curved to direct the electrons to the next dynode. In each dynode, for each electron that hits a dynode, 3 to 6 electrons will come off. This continues as it progresses through the dynodes, and the total amplification is 1 million. For every 1 electron, 1 million comes out at the anode. And then all the electrons are collected at the anode, and that creates the electrical pulse. The high voltage supply is usually 1,000 volts or more. When we talk about the high voltage supply, we're talking about that total potential to the dynodes. The exact voltage is determined by daily calibration. It's really important to do that calibration daily. In newer instruments, the calibration and the constancy are tied together. It's kind of the same thing in the PM2 and the well counter. But you do have the ability to change it and recalibrate it if it's not where it needs to be. Most of the time, if the photo peak is off and it's not calibrated, you can change that voltage supply because it's usually a problem with the voltage. A 1% change in voltage will result in a 10% change in the pulse. That comes for everything that requires a PM tube. If there's a 1% change in the voltage supplied to the dynodes, it will result in a 10% change in the amount of electrons that are actually produced. So this is figure 2.2 in your book. It's showing you this is the high voltage supply to the dynodes, so you can see how that increases with each dynode. And then it's also showing you how that focusing grid helps to direct it to the first dynode, and then how each of these dynodes kind of directs it to the next one and amplifies it as it goes. And then down here, this grayish area is the photocathode, where it enters as a scintillation photon and it's converted to an electron. So another diagram, and I think you guys have seen this one before as well. So the overall process of scintillation detection, the gamma ray will interact with the crystal, electrons move to the conduction band and produce scintillation photons and they're returned to ground state. That's just another way of explaining the photoelectric effect that occurs. The electrons will basically the whole atom absorbs the radiation, electrons get excited and move into a different energy shell, and then as they return to their ground state, it releases a photoelectron, a scintillation photon. So the scintillation photons are absorbed by the photocathode of the PM tube, and the PM tube produces the electronic signal whose size is proportional to the gamma ray energy. So the height of the pulse of the electronic signal is proportional to the gamma ray energy that initially interacted with the crystal. Then you have the preamp and the amplifier. First, the signal goes to the preamp. This is attached directly to the back of the PM tube, directly to the anode, and it minimizes the signal distortion that's coming out. There's a lot of weird things that can happen in the PM tube. We're showing you a very simple diagram, but in reality, there's electronic noise, there's fluctuations in the high voltage supply that will affect the pulse. There's scattering and things like that that may occur within the tube. So that pulse that comes out of there is really rough. And the preamp is just going to smooth it out a little bit and create and shape a more measurable pulse. It actually boosts the signal just a teeny bit too, so that it prepares it for the amplifier. And then the amplifier really amplifies it a lot. And then in doing so, it also smooths out the signal a little bit more. And then this is controlled by coarse and fine gain controls. So you can control kind of that smoothness and the amplification of that through the coarse and fine gain controls. On older well counters, this is actually knobs that you can twist, but this is pretty much self-correcting in the really new well counters. Then it goes to the pulse height analyzer. This evaluates the size of the pulse and correlates that with the gamma ray energy. This is where you have upper level and lower level discriminators. These are values that are set by the operator, and they create an energy window of acceptable counts, and it creates an energy spectrum. Now, that whole process is the scintillation process and how scintillation detectors work. So you have the actual scintillation that happens at the crystal, but the entire process is how scintillation detectors work and the process of scintillation detection, because you can't just detect it just after what happens at the crystal. It has to go through all that manipulation before it can really be counted and determined and measured. So everything that happens in the crystal, the PM tubes, the preamp, the amplifier, and the pulse height analyzer are part of the scintillation process. So if you're asked to explain that process of scintillation detection, it includes all of that, all the way through the pulse height analyzer. Now, a single channel analyzer has one lower level discriminator and one upper level discriminator. The values for the window are set by the operator based on the energy of the photon, and all pulses of the same size are sent to the rate meter and counted. All pulses that fall within the window make it to the rate meter and are counted. And I want to make this distinction here because I did see a lot of confusion before with students. It's not only measuring one energy or one photon at a time, it's measuring one window, and you are setting that one window. So you're setting one lower level discriminator and one upper level discriminator. So if you have a single channel analyzer and you're setting a really wide window and you set it anything from 40 keV to 500 keV is going to count. And inside that window, you have a sample that's a mix of technetium and indium and whatever else, and it has multiple photo peaks. It's going to count all of them and contribute them to the count and just spit out a total number of counts that were in that window. If you know it's tech and you only want to count tech, you can set that window around 140 keV and it will only count that. But the point is, with the single channel analyzer, you can only set one window and you control that. So if you don't know what you're counting, you typically would set a wide window, and then it won't be able to really tell you specifically what you're counting. It's just going to tell you the total counts there. The multi-channel analyzers, on the other hand, can count more than one window at a time, and it assigns them to these preset bins, and you get this wide spectrum graph usually that's presented, and you can see everything if you have multiple photo peaks, you can see them, but you can also set it to count more than one window. The scalar timer then counts the accepted pulses and tracks the time. And so this is just kind of summarizing. We've covered this before. This is figure 2.7 in your book, but it's showing you the PM tube output is really rough. Preamplifier smooths that out and also shapes it a little bit. Amplifier really smooths it out and amplifies it even more. This is where we have the upper and lower level discriminator set at the pulse height analyzer. And then what comes out of the pulse height analyzer is only what fell within that window. So most well counters have 5 centimeters of lead surrounding the detector. This reduces background radiation to us. It also reflects and directs those photons that didn't interact with the crystal back to the crystal. Energy resolution is poorer because reflection and scattering light by the well counter occurs inside the detector crystal and between the crystal and the PM tube. So the energy resolution is a little bit worse with well counters, but the overall efficiency of the instrument is a lot higher. The energy spectrum, also called the pulse height spectrum, we've talked about before. Remember, the x-axis is the pulse height, which correlates to or corresponds to the energy of the photon. And then the y-axis is the number of photons that are being counted. The photo peak is the highest peak, and that will correlate to the energy of the photon being measured. You might have more than one photo peak, especially if you have a wide window, because you might be, there will always be a photo peak down around 40 keV or so. That's just characteristic X-rays. That's just background radiation. So your photo peak then will be the highest peak, and it should correlate with the energy being measured with that other room background photo peak set aside. Peak broadening is both a good thing and a bad thing. It allows for better counting of photons at close energies, but if your peak is too broad, then it's a sign that maybe it has less energy resolution than it should. Calibration with the single channel analyzer consists of setting the desired energy window and then increasing the high voltage to the PM tubes to get the maximum counts within a preset energy window. With a multi-channel analyzer, it will display the energy on a pulse height spectrum, and you can tweak the high voltage to put the top of the photo peak in the middle of the preset window. So with the single channel analyzer, you don't really see that spectrum graph, you just see the total count. And then you have to increase the high voltage with the typically little knobs until you get the maximum counts. So that might take a little bit of trial and error to get it set there. And the older systems, older well counters might be like that. Typically you have it set and you don't really want to change it. And then you do get daily calibrations, and it's essentially like a constancy, but the daily calibrations just to make sure that nothing has changed. And then you can adjust the high voltage if you need to. And we covered this when we talked about pulse height spectrometry. This is showing you the effect of the high voltage has on the calibration. And this refers mostly to the single channel analyzers, the really old well counters, where you would need to move and adjust the high voltage supply to get the maximum number of counts. If your high voltage supply is too low and you're not getting the maximum counts, you adjust it up until you do. And then if you adjust it too far and turn the high voltage supply up too far, you shift the photo peak too far to the right. And it's erroneously like amplifying the energy, so it doesn't really correspond. If this was technetium, this might be falling at like 160 or 170 keV now. And so the number of counts that you counted is going to drop drastically. So as you're calibrating it, it's a little bit of trial and error, turning those knobs just a little teeny tiny bit till you get the maximum counts. Now the output of each detector event is 1 count. We express all of these as counts per minute, sometimes as counts per second, but typically it's always counts per minute that we work with. And the statistic variability of multi-measurements of a single source will kind of lead us to average that out over a minute. So that's why we typically do it as counts per minute. And counts per seconds is going to fluctuate a lot more. The configurations, the organ probe with the flat field collimator and positioning distance rod. We'll talk about the well counter or the uptake probe next lesson. And then the well counter is for samples that are in test tubes, and it can count less than 1 microcurie. Now remember, this is a gas detector for our dose calibrator. Our dose calibrator was only accurate down to about 20 microcuries, whereas this well counter is accurate and can measure less than 1 microcurie. So it's much more sensitive than the dose calibrator. Peak broadening is the main source of statistical variation in the number of electrons that are produced by the photocathode. So if we're measuring 140 keV, we get a peak or a curve. We don't really get a straight line. And that's because there's some statistical variation that some of those 140 keVs might get registered as 130 or 146 or something like that. And so there's more of a statistical variation that's occurring. And this is one of the reasons that we set a window, usually 15 to 20% window around the desired photo peak. And remember, a 15% window ends up being plus or minus 7.5%, and a 20% window ends up being plus or minus 10% because you're measuring 10% above and 10% below for a total 20% window. Energy resolution is the ability of a detector to distinguish between photons of closely spaced energies. And the full width half max is a measure of energy resolution. It's a measure of scintillation detector function, and it decreases as the gamma ray energy increases. The daily tests on the well counter are calibration and constancy, which in the newer instruments it's doing that at the same time. And then infrequent tests would be energy resolution, where it measures the full width half max quarterly. The chi-square test, which is also done quarterly, and then the detector efficiency and the minimum detectable activity are both done annually. There are some well counters which are capable of counting multiple samples at a given time. This is an older one up here in the left. And these other ones are more kind of digital, electronic, will produce a big spectrum graph and really analyze for you. And the one in the top left is small enough to sit on a counter. The other ones are really much bigger. These multiple sample well counters come in handy if you are counting a lot of tests at the same time. And they were used a lot back in the old days of nuclear medicine when you did a lot of tissue sampling and you had a lot of multiple test tubes to count. There's a test that we do where it's not as common anymore. You have to test pledgets that were up in a patient's sinuses to look for a cerebral spinal fluid leak. And in that, the person may have 20 or so pledgets in their sinuses, and each one of those would have to go in their own test tube and be counted. So if you're doing that type of study, a multi-sample well counter comes in handy. Also, if you have a very large department where you're doing a lot of wipe testing, and you're doing your weekly wipes and you have 20, 30 wipes, then it's really nice to have a multi-sample well counter because you can set all your test tubes in and start it and kind of walk away and it will print out a report for you. So that's really handy for that. But these multi-sample well counters do have some problems with them. One of the disadvantages is that if you have, 25 samples that are below background with no removable contamination, and you have one that's really hot, then you will have some cross counting that occurs where it'll increase the background within that instrument, and so it will kind of carry on over to the samples that aren't contaminated. So it could look like more of them are contaminated than are. You might have to isolate the one that's really showing up as hot and kind of discard that. Not discard it, but set it aside and see if any of the rest of them are. And that can make it challenging to get an accurate reading because that background can kind of spill over in the instrument. We also have liquid scintillation detectors. You don't see these very often either. These are basically, the scintillator is dissolved in a solvent in glass or plastic vial, and the sample is added to that mixture. And then the vial is then placed in an enclosure between two PM tubes to detect it. This is really great for beta, and even alpha can be counted this way. It's not as efficient because of the glass or plastic vial, but it can be. It is inefficient for gamma or X-rays though. So really this is mostly done where you see a lot of beta. Now we will cover the actual math and the well counter QC at a later date. This is just provided as an overview. So, like I said, the quality control, daily calibration, and constancy, which are lumped together kind of as the same test. And then the infrequent tests of energy resolution, chi-square, and the detector efficiency, as well as the minimum detectable activity. So the first daily QC check is calibration, also known as peaking. And I want to point out a couple things with this. Really what you're doing is checking the high voltage supply. With single channel analyzers, this calibration is set and you don't want to change it. You just need to check it. If there's a problem with it, you can adjust it if you need to, but you're just checking it. You don't want to play with those knobs or change it. With multi-channel analyzers, you do peak it, but you're essentially checking the high voltage supply. These multi-channel analyzers and the newer well counters will auto calibrate themselves. When you do the high voltage check, they will shift the photo peak to make sure that it's in the window and where it's supposed to be. So the check takes about 2 seconds and it's part of the daily QC. You have to know that it's happening, but it's tied into the constancy on the newer well counters. The purpose of the calibration is to ensure that the high voltage supply to the diodes is appropriate. It's where it's supposed to be. So on the single channel analyzers, you don't really see anything. You're just checking it as part of doing your constancy. But the multi-channel analyzers, you can see the spectrum graph, so you can actually see where the peak falls. And you can kind of see it auto-calibrating and shifting that peak a little bit if it needs to. The method is very dependent on the model, but you select the high voltage or calibration selector button, and modern detectors will show you the graph or the peak. It should be consistent from day to day. If you notice that your well counter is failing daily QC, or if the power goes out, and you need to use the well counter, you should repeat the high voltage supply check or the calibration to make sure, because if it had a voltage fluctuation, it may take it a minute to kind of settle back in. The peak will be centered on the energy for the radionuclide, and or the voltage will be displayed and consistent from day to day. And the fluctuating result could be an unstable high voltage supply. This could be within the instrument, or it could be coming from the outlet or the electrical supply in the building. I have seen this a lot if there's construction happening in the building, that especially if they're doing anything with the electric in the building, it will cause the high voltage supply to be a little bit unstable coming out of the outlets. and then that causes the high voltage supply to the well counter to be a little unstable. There's a gradual shift from a loss of coupling with the PM tube or loss of the hermetic seal that will also lead to fluctuations in the way that it's calibrated. So constancy, also checking sensitivity. We really just call it constancy, but it's also called sensitivity sometimes. The purpose is to verify the overall stability and accuracy of the device. Kind of the same constancy we've already talked about with the gas detectors. You're looking at its stability over time from day to day and making sure it's the same. So the method is to perform a background check by counting with no sources present. Count a long-lived source, usually 100, that should say microcuries. It looks like it converted the mu to an N. But you count with a long-lived source that's usually about 100 microcuries of cesium, and then record the net counts to compare it to the previous results. So remember, net counts, you're subtracting the source from the background. You're just eliminating the background as part of the count. That's what your net count is. And the expected results should be plus or minus 10% of the previous reading. Some troubleshooting for constancy, you want to make sure that the QC source was inserted properly. I've seen people put the source upside down. With those rod sources, there's a black part at the end. That's where the actual source is. The black part has to go down. Make sure that there's no other sources of activity nearby. Use the same source every single day. More than 10% difference usually indicates that there's a problem with the high voltage. If it's a low reading, this could be incorrect high voltage setting or incorrect calibration, incorrect threshold or window setting, and the source may be improperly placed or too far from the crystal. If it's a higher than expected reading, that's probably from an outside source nearby. Typically, this is patient doses or a flood source or contamination to the well outside of the instrument. The chi-square, the purpose is to evaluate the statistical variations of the instrument. There are differences, you're basically looking if the normal differences that are there are normal statistic variation or instability with the instrument. For chi-square, you count the same sample 10 times and then calculate a chi-square. Newer instruments will do this for you, but you do have to do it by hand. And then the expected results, there's a p-value of 0.9 to 0.1 that is acceptable. And then that basically corresponds to the 90% confidence level or plus or minus 10%. The troubleshooting, a p-value less than 0.1 indicates a malfunction or too much variation. And a p-value greater than 0.9 is too perfect and indicates that there's something electrical happening with background noise. So the chi-square, we'll talk about this math later, but it's a summation. This E is the summation symbol. And basically each sample gets counted. You do the square root, divide by the mean. That's what that should be there. I think this is a typo. And then N is the number of samples used. You calculate the degrees of freedom by the number -1. And then you do the standard deviation squared divided by the number or the mean. And that ends up being your chi-square. This is a very long math problem, so we'll talk about that at a later time. This is just an example. These are like 10 samples that you got, and then you'll calculate them out and see if your how your chi-square falls. Energy resolution is another one that's done fairly relatively frequently. It's done quarterly, and the purpose is to examine the sharpness or broadness of the peak. And how well does basically that well counter measure cesium as 662 keV. You will assay the source with an open window. So you have a really open window from typically 40 keV to about 800 keV. And then It'll vary slightly per instrument or radionuclide, but the energy resolution should fall between 8 to 12%. Less than 7% or less than 10% is best. And I've noticed on the newer well counters, it's not uncommon for that resolution to be about 6 or 7% just because they have a little bit better energy resolution. And that's okay. That's not saying that it's bad. It's just typical for it to be around 8 to 12. Troubleshooting, if there's incomplete energy absorption at the crystal, normal variations in high voltage supply, electrical noise, fluctuation to the diodes, all of those things can affect the energy resolution. If a peak is too narrow, it indicates that the instrument may be overcorrecting. We're not detecting normal scintillations. And then a peak that is too broad. So this is where I'm talking about peak broadening being a good thing or a bad thing. If the peak is too narrow, it indicates that the instrument is overcorrecting. So it needs to be a little broad. And then if it's too broad, it results in a malfunction in a system component or from a malfunction. So typically this could be loosening between the crystal and the PM tube, or a degradation of the crystal over time, or inconsistent multiplication within the PM tube. And that could come if you have a lot of high voltage issues that are happening just while in that 1 minute that it's counting. So this is how the detector efficiency is calculated. Detector efficiency determines the percentage of emissions of the source that are actually detected. So how well is that well counter trapping and counting photons? And to do this, you use a source that is, National Institute of Standards and Measurement source to know that it really is a traceable source with known activity. And then you look at the counts per minute divided by the disintegrations per minute times the mean number of disintegrations times 100. So to determine the disintegrations per unit time, you multiply the microcurie amount of the source by disintegrations per second of 1 microcurie of radionuclide, which is a known amount. And then this formula can be used for seconds or minutes. You just need to make sure that your units match. If you're doing counts per minute at the top, you want to do counts per minute everywhere. So this is showing you 1 microcurie is about 2,222,000 disintegrations per minute. So it's asking you what is the well counter efficiency if 1.6 microcurie source produces 664,000 counts per minute. So really all you do is plug that in there. Like I said, we'll do that math at a later date. It's a pretty simple equation. It's just knowing where to plug things in. And then the minimum detectable activity, we won't really go over the math for that because it's beyond really what you need to know. You need to know the theory behind it though. The minimum detectable activity is the lowest activity level that can be detected by the system. The activity present below the minimum detectable activity will not produce a photopeak and will continue to contribute to the background. And the source should be determined for each radionuclide that's used. So it's really used to determine what is acceptable background limits. And this is an annual test that's done where you essentially are just counting the background in the room. So a couple of notes, well counters are used daily for package receipt, weekly for wipe test, and then anytime removable contamination needs to be evaluated. So anytime there's a spill. The well counter is the most sensitive instrument we have, and this is due to the geometric efficiency. It is important to remove other sources from the area to ensure that your counting to make sure that all your counting is the source and not any other sources in the background. Because the instrument is really sensitive, if you have sources out in the area when you're doing the well count testing, it will impact your count. And then you also want to ensure that the source you're counting is all the way in the well so that it's accurate. If you have it kind of cattywampus and it's hanging out or it's not in there all the way, then that will affect the geometric efficiency and therefore it will affect its accuracy. The multi-channel analyzer and newer instruments produce the full width, half max, and energy resolution for you, and this can actually be calculated with the daily QC. It is important to understand how the instruments function so you can easily troubleshoot if any errors do occur. And that's it. We'll talk about well counter math at a later time. And let me know if you guys have any questions.